So last class we discussed thermal energy, and we said that when a hot and cold object were brought in contact with each other, thermal energy would be transferred from the hotter one to the colder one. Well, what are the physical mechanisms by which this thermal energy is transferred? It turns out there's three. There is conduction, which is transfer by direct physical contact. You put them touching each other. Then there's convective transport, which is transfer of thermal energy by a moving fluid. So, for instance, you warm up some air in your furnace, then you blow it with the fan, and that takes thermal energy to all the rooms of your house. Another example in the biological context is you do some exercise, that warms up your muscles, the blood flows through your muscles, absorbs that thermal energy, and then takes it to your skin for dissipation to the environment. Finally, there's radiative transfer, which works through the vacuum of space, and that's transferred by electromagnetic radiation. And typically, for most temperatures of interest for most temperatures of interest, the electromagnetic energy is going to be mostly in the infrared part of the spectrum. So those are the three means of thermal energy transfer that we're going to look at in this class: conduction, convection, and radiation. We'll start with conduction. We'll start with Fourier's law of conduction. And what Fourier's law says is that we analyze, say, the flow of thermal energy through a slab of material. And Fourier's law says that the thermal energy flow through that material depends on a few things. First of all, it depends on the temperature difference across the material. That's delta T. So with a greater temperature difference, you get more thermal energy transfer. It depends on the area of the slab A. With a greater area, you get more thermal energy transfer. It varies inversely with the thickness, because a thicker material has a smaller rate. That's inverse variation. I'll use D for thickness because I'm going to have T for time and T for thickness, and T for temperature, rather. So I'll use D for thickness. The last thing that influences this is the material. And there's a constant known as K, which is the conductivity, and the rate of flow of thermal energy varies directly with that conductivity. So let's build Fourier's law. It says that the rate of thermal energy transfer, which is the ratio or the amount of thermal energy transfer per unit time, varies directly with, as we just discussed, the material's conductivity, the area of the slab, the temperature difference across, and inversely with the thickness. And these are all the units. The units of these three quantities are familiar to you. K is joules per second centigrade meter, or you can write it as watts, because a watt's a joule per second, per meter Kelvin, because a temperature difference of a degree centigrade will also be a temperature difference of a degree Kelvin. Now, this is a rate of heat flow. Recall, for fluid theory, we defined the volume rate of flow as being the cross-sectional area times the speed, and that was the ratio of volume to time in cubic meters per second. This is a similar rate of flow, but it's the joules per second of thermal energy flow. So that's our first principle for today. It's the principle of conductive thermal energy transfer through a slab of material. Now, let's talk a little bit about the thermal conductivity K. So if K is big, that's a good conductor. So what's an example of a good conductor of thermal energy? Well, that would be something metallic. That's why we make pots out of metal. If K is small, then we're dealing with something that's an insulator. That may be, say, like a piece of foam, or body fat is a good insulator. So we can mix and match here. We could say K for steel, that's a conductor, it should be big. K for fiberglass insulation, that's an insulator, that should be really small. And then the K value for glass, well, that's probably in between. And so these are some typical values, and we will use values like this in the problems that we're going to be solving today. So here's a typical example. So we've got a stove element on your stove, and you're putting a pot of water on it. And thermal energy is going to flow through the bottom of the pot into the water, and we're boiling the water, and at STP, boiling happens at 100 degrees, and we're told the element's at 220. So we see what the temperature difference is across the bottom. Now, the bottom is going to be circular in cross-section. So we've got pi r squared for that area. So we want to find the rate of heat flow. So that's the amount of joules per second of thermal energy flow. That's conductivity, area, temperature difference divided by thickness. So it's steel, so we look back at the previous page and say that was 80 watts per meter Kelvin, or 80 joules per second centigrade meter. Cross-sectional area is pi r squared. R is the radius of the pot. That's given as 10 centimeters. And then temperature difference, we said, was 120 degrees centigrade, or 120 Kelvin, divided by the thickness, which is 1 centimeter thick. And then this is the rate of thermal energy transfer. Now, as the thermal energy comes into the boiling water, it's going to produce steam. And we know that the amount of thermal energy, or rather thermal energy that's making steam, is latent heat, and is therefore given by this relationship here. So just delete that email there. If we want to find the rate of production of steam, that means we want to know the mass. The latent heat is going to be 2,256,000 joules to vaporize a kilogram. So we'll find the joules per second and then put it in here, and then we'll solve for the mass. Let's just pause and I'll work that out. So we see that the amount of thermal energy transfer is 30,159 joules each second. So in 1 second, it's 30,159 joules. We divide by the latent heat, and then this will tell us convert from joules per second into kilograms per second. So it's 0.13, or it's 13.3 grams per second. And so that's the amount of steam that we're producing. So we know there's 30,000 joules going into the pot each second, so that tells us that 13 grams of steam are being produced. Next example, this is an interesting one here for historical reasons. Kelvin estimated the age of the Earth by imagining that the Earth had started off as a ball of molten rock and had gradually cooled. And so in his mind, there was a layer of crust on the top, and then at the center there was this layer of molten rock. Now, he knew the temperature at which rock melted. He knew it was 1200 degrees. He also knew from coal mines that the temperature dropped at about per 100 meters, about 2 degrees. So that's about 0.02 degrees per meter. So based on that, he was able to work out what the depth was, or what the thickness of the crust is right here. That's D. So this is basically at 0. This was 1200. If it's 0.02 degrees C per meter, and if we've got to reach 1200 C starting at 0 C, what was the depth of the crust? Let's call that the depth of the crust. So cross-multiplying, we see that it was about 60,000 meters, or about 60 kilometers of crust, and that's not far wrong. That's a pretty reasonable estimate. So next he said, all right, well, if we started off, so this is the 60,000 meters we worked out, by the way, if we started off then with a totally molten Earth, and we've ended up sometime later looking like this, how much thermal energy has been lost to space? So he said each one of these layers of rock at a given depth, right? Say we're at some depth that's less than the 60,000. It's cooled down from 1200 down to its current temperature. So that is the temperature change of a given layer of rock. And then the ones that are deeper haven't cooled down as much. The ones at the surface have cooled down by 1200. So this is the delta T for that layer. And we're going to say the thickness of the layer is delta D. There's a little delta D. Okay, so for that layer, this one layer here, its amount of thermal energy that has been lost out into space is going to be the mass of the layer times the specific heat capacity of rock times the temperature difference. But for that mass of a layer of rock, a mass is a volume times a density. And the volume of this little slab is going to be the surface area A times the thickness delta D. So for our Q equation, I'm not going to put it there, I'm going to put it here, it's surface area times the thickness times the density of rock, that's the mass value, and now we've got to put in the specific heat of rock and the temperature difference. Now if we rearrange that just a little bit, we've got A, the surface area, rho, the density of rock, C, the specific heat, then we've got delta D, delta T. And if we look on our picture, delta T, delta D is just the area of that little wedge that we drew on there. And we want to, of course, find the total temperature difference, not just for this one little layer, but, sorry, the total energy, not for just this one little layer, but for all the layers of rock. That means we want to add up all of them. So we'll do that by summation. So we're adding up, what was that? That was A, rho, C, delta T, delta D, over all the layers, and I'm using summation notation here. But A, rho, and C are just constants. They're the same for each layer, so we end up adding up delta T, delta D, and as I said earlier, that's the little area of that little wedge. And if you add up all of those little layers, then you end up essentially just finding the area of this triangle, right? Because you'd be adding up this little area, adding up this little area, and that's going to give the area of the triangle, which is half times space times height. So we end up with A, rho, C, then 1/2 the temperature, I don't know, temperature of molten rock, and then the depth of the crust. So this is 1200, and that's the 60 kilometers, and they're constants. So that's the total amount of thermal energy that's left the Earth as it has cooled down from the molten state. Well, now we could use Fourier's law, and we could say we know how much thermal energy is left. We'll assume that rate's been constant. We know the thermal conductivity of rock. We should be able to solve for time. And this ratio right here of temperature change over distance, that is just that thermal gradient that they found from coal mines, that for every 100 meters, it went about 2 degrees centigrade of temperature increase. Okay, so we can solve then for time t, which is the age of the Earth, by cross-multiplying it up and by cross-multiplying these things down. So this is going to be K, A, and then the temperature gradient, delta T over D. Now the Q constant we got from the other page, that's all the thermal energy that left the Earth as it has cooled down. And then the denominator here is the same. But the interesting thing here is surface area just cancels. We know all these constants now. And so we can substitute in rho, the density of rock, C, the specific heat of rock, the 1200 centigrade, the 60 kilometer depth, the thermal conductivity of rock, and the temperature gradient of 0.02 degrees centigrade per meter, and we can work out the age of the Earth. So I'll punch that through, and then we'll see what we get. Okay, so substituting in all the values and the various units, we end up with 960 trillion seconds, which is about 30 million years, which is a significant amount of time, but it was thought not to be enough time for Darwinian evolution to occur, and as a result, this was used as evidence against Mr. Darwin's theory. Of course, what Kelvin had missed in this calculation, the age of the Earth, was the convective energy transfer, and a better calculation where you assume that due to convective energy transfer that you've got a shell here that's fairly thin, and then you've got a core that is basically at the same temperature, that has been cooling down from some initial temperature T down to its final temperature, with convective currents there ensuring that the temperature is constant. If you do that calculation, you get a much older age for the Earth, on the order of billions of years, which is enough time for Darwin's evolution to occur. But anyhow, this just shows you, this is physics from 150 years ago or so, mid-1800s. This just shows you that with the fairly simple Fourier law of conduction, you can come up with an interesting result, which is the age of the Earth. Biological question, why do animals huddle when it's cold outside? So here, this is a rear view of a cow. So this is in the summertime. In the wintertime, they get much closer together. Why does that make sense? Well, with less exposed surface area, the rate of thermal energy transfer, which depends on the exposed surface area, there's a lower rate of energy loss to the environment. That's why. Okay, so at this point, we're going to pause with conduction, and we'll pick up the conduction notes in class. We'll move on now and say a little bit about convection. We said that convection was the transport of thermal energy by a moving fluid, and so here this just shows this is showing ions passing from muscle cells into the blood, but of course thermal energy also passes from muscle cells into the blood and then can be transported around the body.